Hey guys, quick lesson today on two equilibrium concepts. The first one is something we call reaction quotient, and the second one is solubility product constant. So first let's talk about reaction quotient. So reaction quotient is mathematically the exact same expression as the K expression. So it is for an equation like this one. Let's take the decomposition of potassium pentachloride. So potassium pentachloride, when you add energy, is going to decompose into potassium trichloride and chlorine gas. So all of those are going to be in the gaseous state. So this is our equilibrium reaction. We all know at this point that we can write K for this equation. We would write K equals the concentration of the potassium trichloride times the concentration of the chlorine divided by the concentration of potassium pentachloride. Now, all of those would be the concentrations at equilibrium. We can write the same algebraic expression for Q. So we're just going to take the K here, and we're going to replace it with Q, where Q stands for reaction quotient. This is true at any point in the reaction. This is not just when we're at equilibrium. So we can use reaction quotient to tell us whether we are at equilibrium or whether our reaction is going to shift. We can also use it to tell us how to predict the direction of that shift. And so that's why we use reaction quotient. If Q if we're at equilibrium, Q will equal K, because all those concentrations will be the equilibrium concentrations. And so it makes sense that Q would equal K at equilibrium. Now, we can also compare Q to K at other points. If Q is larger than K, that would mean that we have more of our product than we have and less reactant than we would have at equilibrium. So that means in order for this reaction to reach equilibrium, it's going to need to shift to the left. If, on the other hand, Q is smaller than K, so if Q is smaller than K, that would mean that we have less reactant than we do, or less product than we do at equilibrium. And so it would shift to the right. And there's kind of a little trick that you can learn. I tend to always write Q first, but if you write K first, so if you say K is greater than Q, now we know it's going to shift to the right. I've just rewritten this in the opposite direction, right? And now you can see that the arrow points in the direction that the reaction is going to shift. So again, if we write the K first and K is smaller than Q, it's going to shift left. If K is greater than Q, it'll shift to the right. So this is, we've talked about the understanding. This is kind of a little trick to help you remember. Okay, so let's practice this with one, and we'll move on to solubility equilibrium. So if we take the same equation, here we're going to keep talking about the dissociation or decomposition of potassium pentachloride. So the K for this equation is 4 times 10 to the negative second. So K for this expression is 4.0 times 10 to the negative second. If you're given concentration, so we're told that the concentration of the potassium trichloride equals 8.8 times 10 to the negative third, and we're told that the concentration of the chlorine gas is 2.5 times 10 to the negative second, And the concentration of the phosphorus pentachloride is 3.5 times 10 to the negative third. These are all polarities. Okay, now it's just a matter of writing our Q expression, plugging in these values. So again, potassium trichloride concentration, did I just say potassium phosphorus trichloride? Concentration is 8.8 times 10 to the negative third. The chlorine concentration is 2.5 times 10 to the negative second. And the phosphorus pentachloride is 3.5 times 10 to the negative third. So we're going to write our Q expression. Q equals the phosphorus trichloride concentration times the chlorine concentration divided by the phosphorus pentachloride concentration. And now I'm just going to plug in those values. So we have 8.8 times 10 to the negative third times 2.5 times 10 to the negative second divided by 3.5 times 10 to the negative third. And when we plug all of that into our calculator, we get 6.3 times 10 to the negative second. And we're going to compare this number, the 6.3 times 10 to the negative second, our reaction quotient value, to our K. 6.3 times 10 to the negative second is greater than 4.0 times 10 to the negative second. Since Q is greater than K, in order for our reaction to reach equilibrium, it's going to shift to the left. Okay, so I would say that this will shift left or shift towards products. Now we can take this one step farther because we know that it's going to shift to the left. If they asked us what would happen to the temperature, well, we know that this is an endothermic reaction because we see energy over here on the reactant side. So if this shifts to the left, we're accelerating our exothermic reaction. We're going to produce energy, so it's going to get warmer. So the temperature will increase. Okay, so that's reaction quotient in a nutshell. Let's talk about something called solubility product constant. Before we talk about solubility product constant, let's have a quick review of what it means for something to be soluble. And so way back in November, we talked about solubility and a bunch of solubility rules, and we discussed the fact that when we say that something is soluble, we mean that more than 1 gram of it will dissolve in 100 grams of water. So we learned a whole bunch of rules about what will dissolve and what won't dissolve, and we memorized all those solubility rules in order so we could apply them. And we said these things are soluble and these things are insoluble. So, like so much else in chemistry, now we're going to refine our understanding of that. When we say that something is insoluble, we're saying that less than 1 gram of it will dissolve in 100 grams of water. That doesn't mean that none will dissolve. It just means that very, very little will dissolve. And since when we have a solid, or an insoluble solid, or a slightly soluble solid in contact with water, we know that if it's ionic, that some of it is going to be dissociating. And so we're going to have an equilibrium reaction. So if we were to look at something, remember our solubility rules, we said that hydroxides are insoluble. So let's talk about aluminum hydroxide, right? Okay, so we're going to talk about aluminum hydroxide. Okay. From our solubility rules, we would say that this is an insoluble compound. It's a hydroxide salt, and it's not with a group 1 or a heavy group 2. But what we find is that if we put this in water, that some, just a tiny, tiny bit, but some of it will dissolve, some of it And because it's an ionic compound, when it dissolves, it dissociates. And so this solid, when placed in water, is going to dissociate and give us aluminum ions and hydroxide ions. But since there are 3 hydroxide ions, it's going to give us 3 hydroxide ions. So make sure that when you write these dissociation reactions, that you bring this subscript out in front as a coefficient, because that's not 3 hydroxide ions stuck together. It's 3 hydroxide ions floating around independently in solution. Okay, so we have this new equilibrium expression, which means that we're also going to be able to write an equilibrium constant expression for this. And this one gets a specific name. It's called the solubility product constant. So we abbreviate it still K, still an equilibrium constant, but we give it a little SP for solubility product constant. So that's our solubility product constant. And so the KSP for this reaction, we would write KSP equals the aluminum ion concentration times the hydroxide ion concentration raised to its exponent. Now, why did I leave this out? Because it's a solid, and solids never get written in our equilibrium expressions. So whenever we write a KSP, it's always just going to be the concentrations of the ions raised to their coefficients from the balanced chemical equation. Okay, so we can do a lot of things with solubility product constant. If we're given concentrations, we can determine the value of KSP. If we're given KSP, we can determine the concentrations. If we're given KSP and we're given 2 solutions and we're told that we're going to mix them, we can determine whether or not a precipitate is going to form. So let's start with the easy ones. Let's start with calculating KSP from concentrations. So we're going to keep working with the aluminum hydroxide. So we're going to be given concentrations here. We have the concentration of the aluminum ions is 2.40 times 10 to the negative 9th. Molar. And the concentration of the hydroxide ions is 7.20 times 10 to the negative 9. Okay, and so we're just going to plug these values into this KSP expression. So we have KSP equals 2.40 times 10 to the negative 9 times 7.20 times 10 to the negative 9 cubed. Now we need a calculator. And we get that the KSP equals 8.96, my bad. 8.96 times 10 to the negative 30. Now it's a really, really tiny number, but these were really tiny numbers as well. So, given concentrations, we can calculate KSP. Let's see if we can go the other way. If we're given solubility, can we calculate KSP? So let's look at a new equilibrium expression. And remember with these, no matter how the question is given to you, we're always talking about solubility. So we're always talking about an equilibrium expression that has the solid on the left and the ions as the products. So let's talk about silver chromate. or silver dichromate, sorry. Okay, so this is our solid in water. It's going to dissociate and give us silver ions. But we have 2 of them, so that's going to get a coefficient of 2. And the dichromate ion. So our KSP expression is going to be the silver ion concentration squared times the dichromate ion concentration. Okay, there's our KSP expression, and we're told that the solubility of silver dichromate is 7.8 times 10 to the negative 5th molar. Okay, so that's telling us that 7.8 times 10 to the negative 5th moles of silver dichromate will dissolve in 1 liter of water. So way below that 1 gram per 100 gram threshold, right? So this many moles will dissolve in 1 liter of water, 7.8 times 10 to the negative 5th. So how do we translate this into numbers that are going to fit into our KSP? Well, we have 7.8 times 10 to the negative 5th moles per liter of water of silver dichromate dissolved. That means that that's our concentration of the dichromate ion. But for every one of these that dissolves, I get 2 silver ions, right? So that means that the concentration of the dichromate ion is equal to 7.8 times 10 to the negative 5th. But the concentration of the silver ion is twice that. So it's going to be 15.6 times 10 to the negative 5th, or 1.56 times 10 to the negative 4. Okay, so now we know the concentrations, and we can just plug them into this KSP expression. And so we'll have KSP equals 7, going in the wrong order, 1.56 times 10 to the negative 4th squared times 7.8 times 10 to the negative 5th. So once again, we need a calculator. And we get 1.9 times 10 to the negative 12, and that's our KSP. Okay, so we now know if we're given concentrations, we can calculate KSP. If we're given KSP, we can calculate concentrations. One more application. And this one is the fun one. This one allows us to use Q and K and solubility product constant, put together everything that we've learned, and see if we're going to form a precipitate. Oh, and it makes us go back to molarity and concentrations and dilutions. So we get to put together a whole lot of concepts that we've learned already this week. So if we're given a mixture, so first let's talk about calcium carbonate for just a second. Okay, so we're given this mixture. Oops. A little bit bigger for you guys, a little bit easier to see. Okay. So we're going to talk about calcium carbonate. We're going to talk about mixing. So in this case, we're going to be given 125 milliliters of 0.010 molar calcium chloride. and we're going to be given 100 milliliters, 0.0 milliliters of 0.050 molar. We're going to go with sodium carbonate. Okay. Now, that's soluble and that's soluble. We have calcium chloride and we have sodium carbonate. Now, according to our solubility rules, when we mix these two things, we're going to get, so let's look what happens when we mix these two things. We have our calcium chloride solution and our sodium carbonate solution. And we have a double displacement reaction. This is a one-way reaction. So we're going to have sodium chloride and calcium carbonate. Now, this is where our question really comes in. Do we have enough calcium ions and enough carbonate ions that this is actually going to form a precipitate? Because these are pretty small concentrations, and that's not a lot. So now, in order to answer that question, we need to write our equilibrium expression for calcium carbonate. So, calcium carbonate equilibrium expression. This solid is going to give me calcium ions and carbonate ions. And the K expression and the Q expression for this equation is Q equals calcium ion concentration times carbonate ion concentration. So now we know the Q expression, calcium ion concentration times carbonate ion concentration, and we know that if Q is bigger than K, that means that equilibrium needs to shift back towards reactants, which means that if Q is bigger than K, we would get a precipitate. But if Q is smaller than K, we won't get a precipitate. So Q greater than K, we get a precipitate. Q is smaller than K, we don't get a precipitate. So we need to figure out Q to tell us whether or not we're going to have a precipitate. So that means I need the concentration of calcium ions and I need the concentration of carbonate ions. I don't have that. I have this. I have the concentration of calcium chloride and I have the concentration of sodium carbonate. But this is before they're mixed, right? And I've got to mix them. So now we've got to think about, okay, what's the concentration going to be after I mix them? Well, when I mix these two things together, the number of moles of each of the ionic compounds doesn't change, but the amount of water does, because I'm going from 125 milliliters to a combined 225 milliliters, from 100 milliliters to a combined 225 milliliters. So we're going to use the idea that concentration, so molarity times the initial volume divided by the final volume equals our new molarity. So this is our initial and you guys might remember this from our dilution equation, M1V1 equals M2V2. So I've just rearranged it so that we're solving for the final molarity. So concentration of calcium ions, let's see. Calcium ion concentration is going to equal 125 milliliters times 0.010 molar divided by 125 plus 100 milliliters. You guys can see that the milliliters are going to cancel out and give me molarity. We're going to do the same thing for the carbonate ion concentration. So we have our carbonate ion concentration equals 100 milliliters times 0.050 molar concentration divided by that same 225 milliliters. Let's grab a calculator and see what those values are. Okay, so this is 5 point. We're going to leave this a little bbit big. Sig-wise times 10 to the negative third molar. And this is 2.22 times 10 to the negative second molar. Now we're going to plug these two values into that Q expression. So Q equals 5.56 times 10 to the negative third times 2.22 times 10 to the negative second. And we get that it's 1.2 times 10 to the negative fourth. Oh, we need a K to compare this to. So the KSP for calcium carbonate is 1.4 times 10 to the negative 8. So since 1.2 times 10 to the negative fourth is significantly larger than 1.4 times 10 to the negative 8, this will in fact cause the formation of a precipitate. So we would say that a precipitate forms. Okay, I hope this is helpful. If you guys have questions, let me know.